Hello, welcome to today's maths tutorial video where I'm going to be showing you how to find the equations of tangents and normals to a curve. But what am I talking about when I mention that word tangent? Well, if you start off with a curve, then a tangent is going to be a straight line that's placed in a way such that it is going to almost just brush past the curve rather than fully cutting through it. That means that the line that we're going to call the tangent is going to have the same gradient as the curve at that point at which it's intersecting that curve. Therefore, this also just gives us a clue as to how we're going to find the equation of a tangent. Because it's just a straight line, we're going to use the same method that we always use for finding equations of straight lines, which is y minus y1 equals m lots of x minus x1, which is therefore just going to require us to know a point on the line as well as the gradient of the line. For the point on the line, well, it's just going to be that point that it shares in common with the curve, the point at which the line is a tangent to the curve at. And then also we need the gradient of the line, but that's just going to be the same as the gradient of the curve at that point they share as well. So therefore, that's also going to make use of differentiation to help us find the gradient of the curve at a specific point. But what about a normal? Well, it's going to be similar to a tangent in some ways insofar as it's to do with a curve and then having a straight line, but instead of having the straight line sharing the same gradient as the curve at the point at which it's brushing past, a normal is drawn so that it is 90 degrees or perpendicular to the curve at the point at which it's intersecting. That means also, as a side effect, a normal is always going to be 90 degrees to the tangent to the curve at that same point as well. Therefore, again, very similar to find as a tangent, you're going to find the equation of a straight line, but instead of just using the gradient of the curve, you're going to do the negative reciprocal of that gradient to turn it into the gradient that is 90 degrees to that. So let's now take a look at a couple of examples so we can get an idea of this process. We've been given the equation of a curve. We're told to find a tangent, so we know it's got the same gradient as the curve at this point that we're finding it at, and this is the specific point we're finding the tangent to the curve at. So therefore, what we need to do is realize it's a straight line, so we need a point and a gradient to find the point. Well, of course, it might be easy to go, well, we've got that already, but not entirely true. We've only got the x-coordinate of the point that we need. We need the y-coordinate as well. So to find that, we're going to plug x equals 2 into the equation of the curve. So therefore, we're working this calculation out. This also gives us a reminder about why it's so important to make sure you're using proper notation with equations, because the notation is meant to help you out. I need to find a y-coordinate, so therefore I'm using the equation that's y equals. Not to be confused with dy dx equals, because that's gradient. But anyway, therefore, plugging that in and working it out, we're going to get, big numbers, 48, take away 20, which is 28. Cool, so that's the first one done. And then we're also going to need to find the gradient of the curve at that specific point, because that's the point at which the tangent will share the same gradient as the curve. So therefore, to find the gradient of the curve, get differentiation involved. So times by the power, take 1 off the power, then effectively times by the power, take 1 off the power, but hopefully you are aware of the quick trick, which is basically however many lots of just x to the power of 1 effectively, or just x, you just get rid of the x when differentiating. But therefore, if we want to find the gradient specifically at x equals 2, we've got to plug in x equals 2 into that equation for dy dx. So therefore, we're now calculating this, which is going to come to, goodness me, 72 take away 10, which is 62. Nice. So we've now got all the information we need to be able to find the equation of the tangent, because we've got the gradient of the tangent and we've got the point, the coordinates of the point that lies on the tangent. So therefore, it's going to be y minus our y-coordinate equals the gradient lots of x minus the x-coordinate. And then we have not been told what format we need to leave the line in, but hey, stuff it, I'm going to leave it in the format y equals mx plus c, because that just feels natural to do. So therefore, we're going to have 62 lots of x minus 124 plus 28 after moving on to the other side, meaning we get a final answer of y equals 62x and then minus 96. And there we go, first example done. On to the second example. Of course, they've given us the equation of the curve once again, not entirely surprising, but this time they want us to find the equation of the normal to the curve, which is important to note because it means we know we don't just want the gradient of the curve, we want the gradient that's perpendicular to the curve at the point we're finding the normal. And the point we're finding the normal at on the curve is this point here, which interestingly has been given to us as both the x coordinate and the y coordinate, which is good because it means we have all the coordinates we need already. Always important to be adaptable. Sometimes they'll give you both, so don't waste time by working out the other coordinate because it's already been given, but also be adaptable like before in terms of if they have only given you one of them, then do work out the other one using the correct equation. But therefore the first thing we're going to do is we're going to find the gradient of the curve using dy dx. So therefore we're going to differentiate. So therefore times by the power, take 1 off the power, times by the power, take 1 off the power, and then technically the same thing happens with the minus 7, but in reality it just disappears. So therefore we can now find what dy dx is specifically at x equals 3, because that's the point at which we want to find the normal. So if we do that, we end up with this. And therefore that's going to be 30 take away 1/3, and that is going to be 89 over 3. However, it'd be very easy to make the mistake of just using that gradient, but that would be therefore finding a tangent. We want to find a normal, so therefore the gradient of the normal, if we write that down, is going to be 90 degrees to that gradient of 89 over 3, which could be simply found by doing minus 1 divided by the gradient of the curve, or the gradient of the tangent. In other words, the negative reciprocal. So therefore, of course, we've got the minus sign out the front, but doing 1 divided by a fraction flips the fraction upside down, like so. Therefore, we now have all the information we need to be able to find the equation of the normal, so we're going to use y minus y1, using the y coordinate given to us in the question, our gradient, and then also x minus the x coordinate given to us in the question. All we've got to do now is rearrange this equation line so that it's in the format requested in the question, which is ax plus by plus c equals 0. So all the algebra's got to be on one side of the equation, but then also a, b, and c have to be integers. So therefore we don't like the fact we've got that fraction there currently, so we're going to have to multiply both sides by 89 to eliminate that fraction. I like to do that at this stage as a personal preference. And then with a little help from a calculator, you can multiply out the brackets to get 89y. That bit shouldn't use a calculator, but 89 times by 39 is 3,471. And then minus 3 times by x is minus 3x. And then plus 9, watch out for the minus times by the minus. Moving everything over to one side of the equation, I'm going to move everything over to the left-hand side. We're going to end up with 3x plus 89y. And then we are going to be taking away 9 from both sides, which will lead to minus 3,480 equals 0. And therefore, we're done with example 2. But before we end the video, a couple of extra things I do want to note. First of all, to do with language, you might have heard me use this language in this video or in other videos where I'm talking about tangents. But basically, I want to draw your attention to this language about a tangent to a curve being tangent to a curve at a specific point, because it's at that specific point that the tangent shares the same gradient as the curve, and it's only at that particular point. Now, to some of you, that might seem a bit of a moot point, just because, for instance, if you're dealing with a circle or a quadratic, a tangent is already guaranteed to only intersect those types of curves exactly once. So therefore, the only point of intersection is the point at which the curve has the same gradient as the tangent, without having to use this very specific language of saying the point at which the line is a tangent to the curve. But the reason we still do use that language is because there are some cases where a tangent will intersect a curve more than once. For instance, a cubic is a good example of this. The tangent doesn't have the same gradient as the curve at both of those points of intersection. It only shares the same gradient as the curve at the point at which we describe it as being the tangent to the curve at that point. So that's the one I've highlighted right there. Whereas you can clearly see at this other point of intersection, the tangent and the curve do not share the same gradient as each other. So that's worth bearing in mind. Okay, that's all I wanted to cover in today's video. I hope you found it useful, and I'll see you in a future video. Goodbye!